All right. New chapter today. Jumping now, the next chapter is on number theory. Roughly speaking, what is number theory? It's basically an analysis of the integers and the rationals, basically limiting ourselves to the axioms of arithmetic for those of you who have done more with me. So now we'll dive into number theory. Our first theorem in number theory is far and away the most important theorem in number theory for the purposes of this class. There will be nothing more important than this theorem. So before we go over the theorem, we're going to do a flashback to third grade.
Okay.
Back in third grade, you learned about division, right? When you were first introduced to division. And if you were a third grader and I said, what's 12 divided by 3, you would have told me 4. Perfect. Now, back when you were in third grade, if I would have said, okay, what's 13 divided by 3, what would you have said?
4 to 3.
You would have said, it doesn't work. It doesn't go into it right. And the fourth grader would have laughed at you and said, it works just fine. The answer is, it's 3 with a remainder of 1. Right? Something like that. And so now we have advanced to fourth grade mathematics. What you did right here is all this is going to be. We called this 3 right here the quotient, and we called this 1 the remainder. That's all we're going to be doing today. Right there. That's it.
Are you for real?
I'm for real. It's that simple.
Sweet.
Now, this theorem, let's read it. And the theorem is all about this division that we just did right here. In this theorem, this number represents our A. Did I say 3? None of you called me on that.
Oh, it's 4, sorry.
4 with the remainder of 1. That was a test, you all failed. Okay. So, this right here is going to be the A in this theorem. This right here is going to be the B in this theorem. This is going to be the Q for quotient. This is going to be the R for the remainder. A divided by B. We said it's equal to Q and an R. Good so far? Just telling you what these symbols are going to represent. Okay. So let A and B be 2 integers with B greater than 0. We're never going to divide by a negative number.
Why not?
So B is going to be what we're dividing by. Because when you're doing a negative divided by a negative, that's the same as a positive. When you're doing a positive divided by a negative, that's the same as negative divided by a positive.
Oh.
And so we can always limit ourselves to the case where B is always some positive number and we're fine. And we'll handle all cases. Good so far?
Yeah.
Okay. Then, there exists. Have we seen the there exists with an exclamation point before?
Yeah. Well,
That means there exists unique. There exists unique Q and R in the integers such that A is equal to QB plus R, where R has to be a number between 0 and B. Okay, that was a lot to consume, so let's go back to fourth grade and connect it with this. You with me? Over here, you said 13 divided by 3 is equal to 4 with I don't know if I want to use R here for remainder of 1. Maybe I'll just put a I don't know. I don't want confusion. Maybe I'll stick with the R. Understand that this R is not the same as that R. Back in fourth grade, you were told that 13 divided by 3 is 4 remainder 1. And that was the answer. Is there more answers, or is this the only answer?
More.
There can be more.
There can be more. What else is 13 divided by 3 equal to?
4 and a third. 4.3.
Well, that's the same as 4 remainder 1.
Oh, is it?
Yeah.
Yeah. Okay.
You're saying 4 and 1/3. Is there another answer to this question?
So no.
No, that's the only answer. That's the only answer. So back when you were in fourth grade, you said that's the answer, and the teacher said you missed an answer. No, you didn't. Those were all the answers. So we're saying this is the answer and the only answer. This is the only quotient and the only remainder that works for this. That's what this is what we're going to be proving is in general, anytime you're doing a quotient or anytime you're doing division, there's one quotient and one remainder that are the answer. So it's unique. There exists a unique Q and R that answers the problem that we're talking about. Now, rather than writing it this way, we're going to write it this way. How did I know that 13 divided by 3 was 4 with the remainder of 1?
Because 4 times 3 plus 1.
Because 13 is equal to 4 3s plus your remainder. we could fit 4 3s in 13, and then we had 1 left over. This is how you know. That's what this equation is. A is equal to however many B's you can fit into your A plus your remainder. Now, why couldn't I say that 13 divided by 3 was equal to 3 with a remainder of 4?
It's the same as 4 remainder 0. Well, no, it's not.
Because
You can fit another.
3 can fit into 4.
You can fit another 3 in that 4. Right?
Yeah.
And so we require our remainder to be smaller than the number you're dividing by. I can't say what's 100 by 10 divided by 10 and say, well, that's 1 remainder 90. Right? That is invalid. That is incorrect. That is not the answer. Your R, your remainder, cannot be bigger than the number you're dividing by. It has to be smaller than it, and it can be 0. You can have no remainder. Good so far? Okay, so let's read this theorem one more time, and please make sure it makes perfect sense to you. You are going to be using this 100 times from here on out. It's never going away for the rest of class.
Oh, first.
For the rest of class. In fact, I'm even going to hunt you down next year and make sure that the classes you're in require you to know the theorem. So it's never going away. Okay, don't look so scared.
Sorry, we got that.
So let's read it and make sure it makes perfect sense. Let A and B be integers with B greater than 0. What are we going to be looking at? We're essentially looking at A divided by B. That's the intuition for what we're looking at. Then, there exist unique numbers Q and R, such that A is equal to QB's plus R, our remainder. Q is how many times B went into A. Down here, our Q was 4, because 3 goes into 13 4 times. So Q is our quotient, it's how many times B goes into A, and R is our remainder. And our remainder has to be between 0 and B. It cannot be B. It has to be smaller than B. Otherwise, we could have pulled another B out of it. Good? Makes perfect sense. Fantastic. So, let's do some examples, just to make sure we get comfortable with this new equation way of writing it, rather than writing it this way. We want to write it this way. So let's start making that shift in our intuition and get comfortable with it. Okay, well, let's say A is equal to 23, B is equal to 10. Let's write out this equation. So then A is equal to how many B's? What's my quotient? What's my Q? 2. 2 B's plus what's my remainder? 3. Good? Okay, now something a bit trickier than what you saw in 4th grade. So here's what's going to get you a few times. Negative 23 divided by 10.
Negative 2.
So 23 is equal to, how many times does 10 go into negative 23?
Negative 2.
Negative 2 tens
Minus 3.
minus 3. Is that correct? What's our remainder?
But you can't have your remainder negative.
You can't have a negative remainder.
Oh, yeah.
So you can have a bigger.
Negative 3 plus
Oh,
7.
so negative 3 plus 7.
Negative 3 plus 7. How did they do that? They said we're going to take away another 10 here, and we're going to add another 10 here. That's going to be the pattern. So your intuition when you do negative numbers is always going to be something like this. Negative 2 and minus 3. Here's what your intuition is going to want to write. Now you just got to shift around the numbers. Subtract 10 here and add 10 there, and that will fix it for you. Whatever your B is. Subtract another B, so this number is always going to be 1 lower than you think, and then you're always going to add B to this number. So what's 1 lower than negative 2? Negative 3. And so we took away another 10, so we need to add 10 to this, which gives me a plus 7. That will be the thinking over and over again. That will be the biggest trick to all this. Some definitions, just so we have names for these things. Oh, I don't know if I said up here. We call Q the quotient, R the remainder, so I'll be saying that when I'm referencing Q and R. Another definition. Let A be Q and R. B is given up in this theorem. So A and B are the ones we're dividing, Q is the quotient, R is the remainder. Then A div B just gives us a quotient, gives us whatever Q is. And A mod B gives us whatever the remainder is. So if you just care about the quotient, you're talking about A div B. Div short for divided by. And then A mod B means just give me the remainder. For those of you who have ever done programming, this is exactly the mod that you use in programming.
Didn't we cover earlier this year?
No, we did congruence modulus, which is not the same thing. So you've seen stuff like this.
Oh, that's right.
This is a relation. This is an operation.
Got it.
This takes two numbers and spits out a number. This takes two numbers and spits out a number. This was a relation. What did it mean for A to be congruent to B mod 2? It meant 2 divided their difference.
Yeah.
So they're related concepts, and we'll see how they're related throughout number theory, but not the same thing.
Okay.
Okay. So just to help get us comfortable with some of this, let's do some of these. Now I'm just going to go like this, and you're going to answer the problems. So we're going to go across this row, then that row, and this row, then that row. So starting with you, 12 div 3. 4. How many times is 3 going to 12? 4 times. All right, to you. 12 mod 3. What is the remainder? So after we do 12 divided by 3, what's the remainder is what mod cares about. 0. Perfect. All right, next.
4.
13 div 3 is 4. 3 goes into 13 4 times. 13 mod 3?
1.
1. When we divide 13 by 3, our remainder is 1. Good? All right. 23 div 10. How many times does 10 go into 23? Twice. That's all it's asking. What's the quotient part? So this is saying ignore the remainder. What's the answer? 2. Correct. All right. And then 23 mod 10 is? 3. It's saying now all we care about is the remainder. All right. Back to the start. Negative 23 divided by 10. 3? 10 goes into negative 23 3 times?
Well, in order to do what we did earlier, yeah.
Not quite 3. You're thinking correct.
Oh, negative 3.
Negative 3, because that's a negative number. Good.
Yeah.
So negative 3. And then what would our remainder be? 7. You want to say it will be negative 3, and then add whatever you're modding by, which gets us to 7. Good?
Yeah.
All right, next, we're doing 11 mod 3.
2 or 3.
2 or 3, what is it?
3.
Instantly, you can rule out 3 because your remainder can never be as big as what you're dividing by. So you instantly know your answer is either 0, 1, or 2.
Yeah, that's my favorite. 2.
2. How many times does 3 go into 11? 2 times. We don't care about that, but what's the remainder? It goes into it 2 times with a remainder of 2. So
Goes into it 3 times with a remainder of 2.
thank you. 3 times with the remainder of 2. So it's all the remainder is what we care about there. Everyone follow that? You'll get the hang of this after a bit, but it's just a shift. All right, negative 11 mod 3.
1.
1. Negative 11 mod 3 is 1. It's negative 2, you guys. No, it can't be negative 2. Your remainder always has to be greater than 0. So your brain wants to say negative 2. Add whatever you're dividing by to get the correct answer. So what's negative 2 plus 3? 1. Now, if you don't see it that way, let's actually write this out. So negative 11 is equal to how many 3's? How many 3's do we have in negative 11?
3.
Negative 4.
Yeah, not bad.
And then plus 1. What's negative 4 times 3?
Negative 12.
Plus 1.
Negative 11.
So remember, this number is always one lower than what you want. You want to say negative 3, so the answer is negative 4. This answer, you're always adding that number to it. You want to say negative 2, so it's positive 1. Right? You wanted to say this was negative 11 is equal to negative 3 times 3 minus 2. That's what you wanted to say.
Yeah.
3 goes into negative 11, negative 3 times with the remainder of negative 2. Well, our remainder can't be negative, so subtract one more 3 and add a 3.
Hold on, do that again.
Okay. If I were to ask you, back in your 4th grade year, so you're comfortable with the concept of a remainder, to do negative 11 divided by 3. If I asked you to do negative 11 divided by 3, what would you have wanted to say? How many times does 3 go into negative 11? Negative 3 times, with a remainder of negative 2. That's what you would have wanted to say. Using our notation, that's saying negative 11 is equal to negative 3 threes minus 2. Here's our remainder, here's our q. This and this are saying the same thing so far. You with me? Now, our remainder can't be negative. That's one of our restrictions. So, I need this to be positive. So I'm going to add 3 to this. But if I add 3 here, that's going to change my equation and make it not true anymore. I can't just add 3 wherever I want. So I'm also going to take away 3 over here. So I'm going to take away 3 and add 3. Or in other words, I'm adding 0 so it doesn't change my equation. And what's my result? I get negative 11 is equal to, I subtracted another 3, so now we have negative 4 threes, since I took away another one. And then I added 3 to this, gives me a plus 1. So, here's what you wanted to write. This number will always be 1 lower than what you wanted. You'll always have to take away 1 more. And this number, you'll always add whatever you're dividing by to it to get the correct number when it's negatives. That will be the pattern. So, can't remember who we're on. So, negative 11 mod 3. 1. What's the remainder when I divide negative 11 by 3? You want to say negative 2, add 3 to it, gets us 1. Okay, next one. 9 mod 2. 1. That was pretty straightforward, right? Okay, 57 mod 2. Take your time. Remember, you just care about the remainder. You don't care about the quotient.
Is it, hold on. I'm suddenly forgetting.
Girl, I don't know, I'm just searching mine up.
Hold on, I'm getting there. It's 28. It's the remainder.
Oh, I see.
1.
And we only care about the remainder. So, yeah, 28, remainder 1. We just care about the remainder, so the remainder was 1. Alright, 84 mod 2.
There is no remainder, right?
So the remainder is
0.
0. There is a remainder, it's just 0. Always and forever, there's going to be a q and an r no matter what. Just keep that core in your head. Okay, next one. Negative 279, negative 2,791 mod 2. 1. What's the quotient? Who cares? The remainder is all we cared about, and it was 1. 5,764 mod 2. 0. How on earth did he do that so fast? Is this number odd or even? Even. What does it mean to be even? 2 goes into it evenly is the way you're used to hearing it. So the remainder is going to be 0 if it's even, and if it's odd, then it's going to be 1. So modding by 2 is very simple. When you mod by 2, it's going to be a 1 if it's odd, a 0 if it's even. So we love mod 2. Doesn't get easier than that. Good so far? Let me write one trick question really quick for whoever's next. You get the trick question. What's 3,796 mod 1? How many times does 1 go into 3,796? 796 times. And what's the remainder? 0. Your remainder always has to be less than the number you're modding by. And it always has to be greater than or equal to 0. So you're looking for a number less than 1, but greater than or equal to 0. So it's always going to be 0 when you mod by 1. Because 1 will go into any integer, some integer number of times, no remainder. Good? Getting more comfortable with this mod thing? Alright, on to the next one, wherever we left off. More tricky one. Negative 37 div 5. So we're looking for the quotient, not the remainder. How many times does 5 go into negative 37 times?
Negative 8.
Negative 8?
Oh.
It's negative 7, right?
No.
No, it's always one less than what you want it to be. You want it to be negative 7, so obviously it's negative 8. Alright, back around. Negative 37 mod 5. What would the remainder be?
Is that me?
No, it's her. Oh, no. Front row, right?
Yeah.
We went this way. Back to front. We're looking for the remainder. Huh? 3. You want to say the remainder should be negative 2. Add 5 gets us to 3. Alright, negative 21 mod 8.
Oh, I'm thinking.
Okay.
Is it 2?
Close. So, if that were a 21, then you would say your remainder is 5, right?
Oh, okay.
So you want to say the remainder is negative 5, add 8, gets us 3. Okay. Next one, negative 21 div 8.
Negative 3.
Just negative 2 times, right? No, negative 3 times. Always one less than what you think. Alright, 39 mod 13.
12.
12?
I think so. Not good at math.
In a sense, you're close.
13 times.
In another sense, you're as far away as you can be.
Oh, no. It's 0.
It's 0.
Sorry, I didn't know there was a bit of one here.
Yeah, add one more. Or whatever your thinking was. Alright, and finally our last one, 117 div 7. How many times does 7 go into 117? Close, 17 times.
That's cool.
You know it has to end in a 7, because 7 times 7 gets you the 7 at the end. 7 times 7 is...
49.
Oh, oops. I thought about that weird. I thought I put 19 there. So you were right, it's going to be 16. There goes my mental math. Good job. Okay. So there are a bunch of examples using this theorem. This theorem, it's basically dividing. That's all it is. It says pick any two numbers you want. When you take their division, you get one and only one answer. One the quotient, one the remainder. And there's only one right answer. Now we're going to spend pretty much the rest of the class proving this theorem.
Can we take a break when we get to 10?
We can take a break when we get to 14. That's a natural ending spot. Okay.
Right now is a natural ending.
Come on, we're like 15 minutes into class. All right, so let's now prove this theorem. So what am I going to prove?
I thought we already proved the theorem.
No, so far we've just been using it to help you get comfortable with what it's saying. So now I'm going to prove that this is a fact true. So I'm going to prove let A and B be any integers in the world you can think of, as long as B is some number greater than 0. I'm going to prove to you that there are two numbers, and only these two numbers, Q and R, such that A is equal to QB plus R, where R is between 0 and B. So I'm going to prove that every time you solve one of these problems, there's an correct answer, and furthermore, that there's one and only one correct answer. So my proof can be broken up into two parts. I'm going to prove that for any two integers you choose, right? Maybe there are two numbers you can think of that you can't do this division process with. Trying it with a billion numbers doesn't prove it's true.
Right.
So I'm going to prove that it doesn't matter what two integers you choose, this method, always and forever, will give you a correct answer. So that will be the first part of the proof. The second part of the proof will be to show, and it's the only correct answer. There are no other correct answers out there. So I'm going to prove that there is an answer, and then show that it is the only correct answer. That will be the two steps in the proof. Ready with me so far? Okay. So first, I'm going to prove that you can find a Q and R that make this equation true, where R is between 0 and B. So let A and B be any two integers you can think of, as long as B is greater than 0. With me? Okay. Let big A be the set of all A minus some integer multiples of B, of B, for every integer K you can think of. Now, what on earth is this? Let's scribble out an example to the side to help us think this through. So give me two numbers. Give me an A and give me a B. Make your A kind of big. Do it one that you can't easily do in your head.
103.
Okay, 303. And pick a B. Has to be greater than 0.
18.
18. Okay. So, imagine I told you to figure out what's the quotient, what's the remainder. If you were like a little kid doing this, what would you start doing? You start counting how many times you can fit 18 into 303. So you might start at 303 and take away 18 and say that was 1, and then take away another 18 and say that was 2, and keep taking away 18s as many as you can. Right? So you might start out with, well, we can have 303. Now I'm going to take away 18. What's 303 take away 18? 285. Is the 18 going to be too tricky for you guys to do the mental math? Just for the sake of keeping it simple, we'll just make that 20 so we can easily count down and it's easier for you to see what the answer can be. Okay. So you're a little kid and you're trying to count. Okay, let's see how many times 20 goes into 303. So I'll do a 120. Take away 20 from that gets me 283. And then take away another 20 gets me down to 263. Take away another 20 gets me down to 243. And here you'll be counting off on your fingers. Eventually you'll get to the number, we'll just say 43. You'll eventually get to 43. Then you'll write 23. Then you'll write 3. Then you'll write negative 17. Then you'll write, because you didn't know when to stop. But at this point, you've obviously gone too far, right?
Yeah.
And notice what you're writing down. Your answer was however many times you took away that Q, and then this 3 here would have been your remainder. Right? Here's where you should have stopped, once you couldn't have taken away another 20. And that would have been the remainder for the problem that you were solving. Very simple way of doing this, right?
Yeah.
That's what this set A is right here. Big A, we start with little a, the number we're dividing, and we're going to keep subtracting integer multiples of B. So we're going to subtract 1B, subtract 2B, subtract 3B, subtract 4B's, 5, 6, 7, and we're going to do it for all the integers, so we're not going to know when to stop. Okay, that was kind of stupid, and we wrote down a lot of numbers, but we for sure wrote down the number we care about.
Okay.
And I'm going to prove that this number is the number we care about. Remember, I need to come up with some process for always finding that remainder. For any two numbers, A's and B's.
Okay.
And it doesn't matter if it's a stupid, inefficient process. I just need to prove that it does give us a number. Okay, so let big A here be the set of all A minus some integer multiple of B for all integers. And note that this is the set of all possible remainders, one of which is going to be the R we actually care about. The R that is equal to A minus QB. In this case over here, it's going to be that 3. So I'm on the lookout for that 3.
Okay.
Now, how would you describe where that 3 is to me in the set? What is 3 in that set? Tell me what it is.
The smallest.
Is it the smallest number? No, negative 17 is smaller than 3.
The smallest positive number.
It's the smallest positive number. Notice that if we did that for any two different numbers, our remainder, if we wrote out this set, would always be the smallest positive number.
Yeah.
Do you see that?
Yeah, because the number.
Let's just scribble out another example down here, just to make sure this is perfectly clear. We'll do a simpler example here. We'll make A equal to 23, and we'll make B equal to 4. Okay, what would this set look like, this big A set? So big A up here looks like this. Big A down here looks like this. We start with 23 minus 0 fours. Then we're going to subtract 1 4.
19.
Subtract 2 4s.
15. 11.
Sorry.
7, 3, 4, 5.
Right, and we went too far.
Yeah.
But notice, oh shoot, I used a remainder of 3 both times. That's an accident, the fact that the remainder came out 3 both times. But notice that once again, the remainder, if you did 23 divided by 4, your remainder would have been the smallest positive number in the set.
Yeah.
That's the way we're setting it up. We're subtracting b's until we're left with our remainder. Exact way you would have thought about in your head. If I was doing this process, how many b's can I fit into 23? I can fit 4 of them, so you subtract 4 times, and whatever that next number is your remainder.
Can fit 5. You fit 5.
5, sorry. 1, 2, 3, 4, 5, then the next number. Should learn to count, huh? Okay. So, here's the set A in general. Here's it written out concretely in 2 different cases. The point is, somewhere in that set is the remainder we care about, And what is the remainder we care about in that set? You've already said it. It's the smallest positive number. I'm going to say the exact same thing up here. So first thing, I'm going to let big B be A intersected with the naturals. Why would I intersect this set with the naturals?
So you get the positive numbers.
It gets rid of all the negatives. That's all that's doing. It's like filtering out all the negatives. What are the natural numbers?
0, 1.
0, 1, 2, 3, 4, 5, 6. My remainder has to be a natural number, right? It can't be less than 0. So I'm going to take this set. If I were to take this set and intersect it with the naturals. You remember what set intersection is? It has to show up in both sets. What are the numbers that show up in this set and are natural numbers? All the ones that aren't negative. So it gets rid of this, it gets rid of this, it gets rid of this. Right? What are all the numbers that show up in this set and are natural numbers? It gets rid of this, it gets rid of this, it gets rid of this. And so now notice, now getting rid of those numbers is how we got to B. Now inside big B, what is our remainder?
The smallest.
It's the smallest element
Yeah.
in the set. So now I got B. B is A intersected with the naturals. And so now the smallest thing in B is going to be the R that we care about, and I still have to prove that. Now, remember our well-ordering principle? What does the well-ordering principle say?
It has the least element.
What has the least element?
Any set?
The set. that-
Not any set. What's the least element in the integers?
Well, it's natural numbers, but there's a way it's straight. I just can't remember.
Any non-empty subset of the natural numbers has a least element.
Right.
Now, is B a subset of the natural numbers?
Yes.
How do you know?
Intersect with the
Because we intersected it with the natural numbers. So everything that shows up in B had to be a natural number. So it's a subset of the natural numbers.
Right.
So does B have a least element?
Yes.
We don't quite know that yet.
We don't.
No, how do we know B has a least element?
We have to prove something's in there.
We have to prove it's not empty. If we can show it's not empty, then it has a least element. So this is going to be some confusing line of algebra, but all this is saying is there's at least one thing in B. That's all this is saying.
What?
So I found one particular thing in B. What's the thing that's always going to be in B? Remember, B is A intersected with something.
Yeah.
So let's look at A. B is all the positive elements in A. So what is A? A is a set of all little a's minus some integer multiple of B. So if I take A and I subtract negative the absolute value of A and multiply it by B, notice that this has this form. We're doing A minus some integer times B. Now, B we know is
Not 0.
not 0. So it's not only not 0, it's
Greater than 0.
so it's positive.
Yeah.
B is positive. The absolute value of A is
Positive.
positive. Negative, absolute value of A then is
Negative.
negative. A negative times a positive is,
Negative.
when we take A and we subtract a negative, we get a
Positive.
positive. Only if this number is at least as big as A. With me so far? Okay. Since B has to be 1 or bigger, since it's an integer, then this will guarantee us that this thing always comes out bigger than A, because A could have been a negative number.
B can't.
Let me write this concretely for the case that A is, give me a number for A that's negative.
-3.
Well, we want it to be something we can, let's just do A equals negative 23 and B is 4. And let me write out what that exactly is. So now we're looking at negative 23 minus negative, what's the absolute value of negative 23? 23 times B. And all we care about is that it's a positive. This is bigger than that.
Okay.
Good? So this is just that in general, showing that there's at least one positive element. That's all we were showing. For any A and B, this will always be a positive number that fits this pattern. So it will have always shown up in big A, so it will always have shown up in big B. So there is at least one thing in big B. That's all this was saying.
Can we found an actual example? Is that it simply?
Well, you need it to be generic for any A and the B that you choose here.
Okay.
Good?
Yeah.
Okay. So now, we've shown that B, remember what big B is. It's this set now, with all the negatives removed. And we know that the smallest thing in B is what we care about. So, since I showed that B is not empty, then, by the well-ordering principle, B has the least element, we're going to call that R. So I've now found my remainder, and now I need to prove that it fits this form. That it's the thing that satisfies this. Okay. Now, if R was in B, well, since R is in B, what does that mean? Remember that R was calculated this way. So I know that R is equal to A minus some integer times B. And I'm just going to call that integer Q. Since R was in the set A, it had to be calculated this way. When we were doing our R here, how did we get that 3? We started out at 303 and we kept subtracting B's until we got to that number. R can always be expressed as A minus some integer number of B's. So since R was in that set, since R was in B, or since R was in big A, that's where it initially came from, and since B is a subset of the naturals, starting right here. Since R was in B, then there must have been some integer Q, such that R is equal to A minus QB. We had to subtract some integer number of B's from A to get R, because it was ultimately from the set A. Furthermore, since R is in B, and B is a subset of the naturals, R has to be greater than or equal to 0. So I found R, so that R is equal to A minus QB for some integer Q, and R is greater than or equal to 0. What's the last piece of the puzzle we need?
You have to show that R is less than B.
I need to show that R is less than B. That's the last thing I now need to show. I need to show that if you did grab the smallest thing in there, it couldn't have been bigger than 20.
Right.
What would have happened if we would have grabbed a number bigger than 20?
Then the number after it would be a positive number.
Then the number after it would have been our smallest element, not this one.
That wouldn't have been the smallest element instead.
Right. So I'm going to show that if you happen to pick a remainder that was bigger than B, you didn't pick the smallest number, which is what we already agreed R has to be. That's going to be our contradiction. So it remains to show that R has to be less than B. So assume by way of contradiction that R is greater than or equal to B. And what am I going to do? If R was greater than or equal to B, if R was this one, I'm going to say let R prime be this one and show that R prime then is our least element, not R. Contradiction, because R is our least element.
Okay.
So that's the thinking then. So assume by way of contradiction that R is greater than or equal to B. Now remember, what was R? It's just A minus QB, so I'm just doing that substitution. A minus QB is greater than or equal to B.
Okay.
Good? Now, let R prime be the next one in there. How do I get from R to R prime?
Subtract by.
Subtract another 20.
We know that.
Or in other words, up your quotient one. Make your Q one bigger.
Do we know that R prime exists?
No, R prime doesn't exist.
Well.
Right? We're setting up an impossible picture now. You said, what if this was actually your smallest element and it was bigger than B? I'm going to say that it wasn't really my smallest element. You're lying to me. That's impossible. So R has to be our least element. Or so r has to be greater than or equal to b. If it wasn't, then it wasn't our least element, is what we're proving. Okay, so then let r prime be a minus q plus 1b. Let it be the next thing in there. Subtract another 20. Or in other words, up the quotient 1. Good so far? So up the quotient 1 or subtract another b is what our r prime is, the next thing in there. So let r prime be the next thing in there. Now just doing the algebra. So a minus qb. So here's our minus qb. And then we have a minus 1b. Just distributing the negative through both those and multiplying it by b. See the algebra there? Negative qb, negative 1b, negative 1b. Okay. And what is a minus qb equal to?
That is r.
R. So r prime then is equal to r minus b. It's just b away from r.
Right.
If r was 23, then r prime is 3, subtracting another b.
Okay.
Good so far? Since r is greater than or equal to b, then r minus b must be
Greater than 0.
greater than or equal to 0. So since r is greater than or equal to b, r minus b has to be greater than or equal to 0. And r prime is equal to r minus b.
So it's greater than 0.
So r prime has to be greater than or equal to 0. So then r prime is in b, and r prime is less than r, which is a contradiction. Because by definition, by choice, r was the smallest thing in b. That's what we chose r to be. So if r was, where do we start? Right here. If r was greater than or equal to b, then we got that r is not the least element in b, in big B, which we know it is. So there's our contradiction. So therefore, r has to be less than b. Okay, so there we go. We got the last piece now. R is less than b. So what did we do so far? Thus far, we have shown that there are two integers, q and r and z, such that a is equal to qb plus r, where r is between 0 and b. That's what we've shown so far.
Okay.
What are we missing?
The unique
It
part.
remains to show that they're unique. So far I've shown that anytime you pick an a and a b, you can calculate the quotient and the remainder. You can always do that. But I did not show that is the only quotient and remainder you could possibly calculate. That's going to be the second part of this proof now. Okay, so how do we show that a solution is unique? So I say that there's only one solution. You say, you liar, I found another solution. I came up with a different q and a different r that work. Okay? I'm going to show that, no, you're the one lying. You actually chose the exact same q and r as me. So assume by way of contradiction that you did the impossible. That there exists a q prime and an r prime, those are your numbers, such that a is equal to q prime times b plus r prime, so you found the quotient and the remainder. But you're saying that you did not use the exact same two numbers as me. So you're saying either you had a different quotient, or you had a different remainder, or you had different both.
Does that have to be the same b?
Yeah.
Yeah.
But that's the problem. We're saying that we're doing a problem like, 303 divided by 20.
Right.
And I'm saying that the answer is exactly 15 remainder 3, right? You're saying, no, I found another answer. I said, this is the only answer. You're saying, nope, I found a different answer.
Right.
So you must have had a different quotient than me, or you must have had a different remainder than me. Or potentially both. And I'm going to show that, no, you actually picked the exact same two numbers I did. So that's what I'm going to show. So you say you found a different solution where your q's different than mine, or your r is different than mine. I say liar. Let's show that you're lying. Well, a is equal to qb plus r, right? That was my solution. And a is equal to q prime times b plus r prime. That was your solution.
Yeah.
Good so far? Well, since a is equal to that and a is equal to that, then this has to be equal to this. So my q times b plus r has to be equal to your q times b plus your r.
Yeah.
Okay, subtract. I'm basically putting the r's on this side and the q's on that side. So subtract r prime from both sides, puts the negative r prime over here.
Yep.
So moving that over. And subtract the qb from both sides, put the qb over here. I also factor at the same time. Hopefully you can see that.
Yep.
So q prime times b is this one, b times q prime. And then when we move this over, it's a negative. So negative q times b. Good?
Yep.
Okay. So r minus r prime, notice, is equal to b times an integer. No, right? Okay. So r minus r prime is equal to b times some integer. What does that mean? That means that their difference between them is some multiple of b. If you found a different remainder than me, then it had to differ from my remainder by some multiple of b. The difference between our remainders has to be some multiple of b. Because that's how you calculate your remainders. You keep subtracting b's till you get to your remainder.
But doesn't that mean the R prime isn't the least element? Was it similar to what we just did?
Well, now we're doing a separate thing. That was just to prove that one solution exists.
Right. But that seems very similar.
Well, maybe you didn't have to use the least element though. All I showed over here is that the least element does in fact satisfy this. And if you picked an R that didn't satisfy this, then you didn't pick the least element. Well, maybe you didn't have to use the least element, and it still would work. Okay, so whatever the R is that you chose, and the R that I chose, they have to differ from each other by some integer multiple of b. In other words, b has to divide r minus r prime. Has to go into it some integer number of times. Now, whatever our remainders are, we chose them so that they satisfy this condition over here. So I know that my remainder and your remainder, they both have to be greater than or equal to 0, and they both have to be less than b. What is the greatest distance that can exist between r and r prime?
B.
If I tell you that I'm thinking of two numbers between 1 and 10, what is the furthest away those two numbers can be?
Or
9. Right?
Yeah.
If we include both the 1 and the 10.
Right.
Okay. If I have two numbers r and r prime, they're greater than or equal to 0, but they're less than b, what's the furthest apart they could possibly be?
B minus 1.
B minus 1. They can't be a full b apart.
Right.
Okay, so the furthest apart that they can be is b minus 1. So they can't even be 1b apart. But I also know that they have to be an integer multiple of b apart. So you have to be some integer number of b's apart, but you can't even be 1b apart. So how many integer multiples of b can you be apart? 0. It has to be an integer multiple of b, and it can't even be 1. So how many b's apart can you be?
0 B apart.
Which means that there's no distance between them, or in other words, they're the same number. Perfect. So, since r and r prime differ at most by b minus 1, and their difference is a multiple of b, then r minus r prime has to be 0. Or in other words, r has to be equal to r prime. Exact thinking you just went through. Okay, so I showed at the very least you should use the same remainder as me. But maybe had a different quotient. Well, we'll show how that doesn't work. So far I know that the r and the r prime are the same. Now coming back up to where we started. QB plus r has to be equal to q prime times b plus r prime. So rewrite that now. I still know this.
Yeah.
But now I know that my r is equal to your r prime. So I'll subtract those from both sides. And I get q times b is equal to q prime times b. Since b is a number greater than 0, I know I can divide both sides by it. And I get q is equal to q prime. So you're lying about that too. So if you had a solution different from mine, it turns out it was the same as mine. Or in other words, proved by contradiction. Assume that your solution was different than mine, turned out it was the same as mine, contradiction. Therefore, there is no other solution. This is the one and only solution. So you can take comfort in that on your next test. Every problem has one and only one right answer. Phew. Don't have to find multiple answers. So therefore, Q and R are unique. All right, any questions on that? That's the big guy. That's the big theorem of number theory. We will use this theorem over and over and over again. Never going away. So now, let's just do some small corollaries. Corollaries are just small proofs that you basically get for free from it. using this theorem, just get us comfortable with what the theorem says and how to use it. Okay. That gets us stress board. Okay, so let's do a quick corollary, one that we've almost proven. So we're going to prove that every integer is even or odd, not both.
Have we proved this?
No. What did we already prove? We proved that any integer that is even is not odd, and if it's odd, then it's not even. We showed that it can't be both. So we won't bother redoing that part of the proof. That was one of our first proof by contradictions.
Oh, yeah.
Going back to, I don't remember what section that was.
Direct proof with the second
Like
one.
section 20 or something like that. Indirect proof.
Yeah.
Direct proof is just when you follow the implication directly. Might have said reductio ad absurdum. I don't remember if this textbook uses that language.
It does.
But it was like our first example of proof by contradiction.
Okay.
Proving that an integer cannot be both even and odd. And the contradiction was, if it is, then it's not an integer, it came out a fraction. Okay, so now we're going to prove that every integer is even or odd and not both. Let a be any integer. Our job is to show it's both even, it's either even or odd and can't be both. And we've already shown that it cannot be both even and odd, so we're not going to bother with that. Now I'm going to show that it has to be even or odd. We already know it can't be both. Okay. Now using that theorem, a is some integer, right?
Yeah.
So I can divide it by 2. If I take any integer and I divide it by 2, I will get some quotient and I will get some remainder.
Yeah.
I've proven that I can take any integer and I can divide it by any other integer greater than 0, and I will always get a quotient and remainder. One and only one quotient, one and only one remainder.
Yeah.
That's what we've proven so far. You can divide integers. This is crazy. Right?
Yeah.
So I'm going to take a and I'm going to divide it by 2. So then there has to exist a unique quotient and remainder such that a is equal to some number of 2's plus our remainder. I just took a and I divided it by 2. And it's going to give me some quotient and some remainder.
Okay.
What are the restrictions on my remainder?
Less than 2.
R has to be between 0 and b. So if I'm dividing by 2, what is the biggest my remainder can be?
2. Less than 2 plus 1.
1. What's the smallest my remainder can be?
0.
0. And we already did some example problems where we were dividing by 2. And when the remainder came out 0, our number was even. And when it came out 1, our number was odd. And that's exactly what we're thinking we're going to use here. So then there exists a unique quotient and remainder such that a is equal to the quotient number of 2's plus our remainder, where our remainder has to be between 0 and 2, not including 2. Or in other words, our remainder has to be 0, or it has to be 1. If our remainder is 0, if I say that a is equal to 2 times q plus 0, what is a? An even, because it's 2 times an integer. That's even. If I say that a is equal to 2 times q plus 1, what is a? By definition. So if the remainder is 0, a is even. If the remainder is 1, a is odd. And our remainder has to be 0 or 1.
Right.
There has to be one and only one solution to this, satisfying these conditions. So whatever the a is you chose when you divide it by 2, you will get either a remainder of 0 or a remainder of 1. If you got a remainder of 0, it has to be even. If you got a remainder of 1, it has to be odd. So every integer is even or odd. Learn all sorts of new things today. Good? Okay, let's do one more easy proof and then we'll be done. Another corollary. Something we've already said a few times, but now we'll actually prove it. A is congruent to B mod 2. Let's remind ourselves of what that means. What does it mean to say A is congruent to B mod 2? What's the exact definition of that?
Means 2 divides the difference.
2 divides their difference. So let's see. Is 13 congruent to 3 mod 2?
Yes.
That's equivalent to saying, does 2
Yes.
divide 13 minus 3? What's 13 minus 3? 10. Does 2 go into 10 evenly?
Yes.
Yeah, so in that case it worked. Well, is 13 congruent to 4 mod 2? Well, that would have put 4 here. 13 minus 4 is 9. Does 2 go into 9 evenly? No. So that one was not true. If this were, we'll do 26 now. Is it true that 26 is congruent to 4 mod 2?
Yeah.
Well, 26 minus 4 is 22 divided by 2 is 11. It worked.
Just any even, all evens are congruent mod 2, right? I think I got that wrong.
All evens are congruent to each other, mod 2. And all odds are congruent to each other, mod 2.
When you subtract.
And an odd is never congruent to an even, mod 2.
Right.
And an even is never congruent to an odd, mod 2. So what we're going to show is that A is congruent to B mod 2 if and only if they have the same parity. Parity meaning they're both even or they're both odd.
No.
That's what we're going to prove.
Okay.
So let's prove that. Forward direction. So I'm going to show if this is the case, then this is the case, and then we'll do the next direction after. So I'll let A and B be integers such that A is congruent to B mod 2. Okay, 2. What exactly does that mean? What does it mean for A to be congruent to B mod 2?
2 divides A minus B.
2 divides A minus B. So then, I know that 2 divides A minus B. What does it mean for 2 to divide A minus B?
Means that 2 times some integer is equal to A minus B.
It means that 2 times some integer is equal to A minus B. With me so far? Okay, now what?
We can
I'm trying to show that they have the same parity. I'm trying to show that if A is even, B is even, and if A is odd, B is odd.
If you just add B, then you get A is equal to 2k plus B. And then that shows that A is,
Let's solve for one of them. Which one do you want to solve for?
solve for A, it's easy.
Solve for A. 3. Then A is equal to,
2k plus b.
we're going to put the B over here, so 2k plus B. Okay. We're trying to show that they have the same parity.
Yeah.
I need to show that if A is even, B is even, and if A is odd, then B is odd. Or if you're going to think about it this way, then I want to show if A is even, or sorry, if B is even, then A is even, and if B is odd, then A is odd.
Well, if B is even, then you can just rewrite
Four.
A as 2k.
Yeah, let's write it
And
out.
if it's odd, then you can just
So-
write it as 2k plus
If B is equal to, sorry, if B
2k
is even, what do I know? If B is an even number, what do I know?
A is equal to.
What do you know about even numbers?
So you can put 2 times later.
Here's an answer from Merriam-Webster.
Siri's quicker than you guys. Okay. If B is even, if B is an even number, what do we know about it?
That it's equal to 2 times A.
It's equal to 2 times something. That's what it means to be even. You're 2 times an integer, right? Did you say it and I didn't hear you?
No, something just happened. I'm sorry.
Ah. Okay. So, if B is even, then B has to be 2 times an integer.
Yeah.
That's what it means for B to be even. So then that gives me that B is equal to 2 times some integer, I'll say n. So then what is A equal to?
2k plus 1.
A is equal to 2k plus 2m, which can be rewritten as
2 times k plus m.
2 times k plus m. Is even. So I showed if B is even, A is even. Now what do we need to show?
If A is,
If B, we want to do B since we solved for A.
okay, so that'd be odd.
Otherwise you'd have to move around. So if B is odd, then what do I know?
A is equal to 2k plus 2m plus 1.
Well, yeah, let's do it in one step. B then can be expressed as 2m plus 1. That's what it means to be odd. And so then what is A equal to?
2k plus 2m plus 1.
2k plus 2m plus 1, which is equal to, factor the 2 out, 2 times k plus m plus 1, which is 2 times an integer plus 1, is odd. Okay, so we've shown the first direction of this proof. So far I've shown that if A is congruent to B mod 2, then A and B have the same parity. If A is even, B had to be even. If A is odd, B had to be odd. Or we did it the other way. If B is even, A has to be even. If B is odd, A has to be odd. So they have to have the same parity. So we've shown the forward direction. I used the fact that A was congruent to B mod 2. And I showed if one's even, so's the other, and if one's odd, so's the other.
Yeah.
Now we need to go the other direction. This time we need to do, if they have the same parity, then they're congruent to each other mod 2. So now, we're doing this direction.
That seems
So this time let A, B be integers once again, such that they have the same parity. Alright, so I not only have the same parity, but we still have two cases to handle.
Yeah.
Either they're both even or they're both odd. I need to show if they're both even, then they're congruent to each other mod 2. And I need to show if they're both odd, then they're congruent to each other mod 2. Right?
Yeah.
So, 7. If A and B are even, what do I know?
They're equal to 2k and 2n.
Perfect. Then I can say A is equal to 2 times some integer, and B is equal to 2 times some other integer. Right? Then what does that give me?
Then their difference each visible value.
Then A minus B is equal to 2m minus 2n is equal to 2 times m minus n, 2 times some integer.
Means that 2 divides that.
Which gives me that 2 divides A minus B, which gives me that A is congruent to B mod 2. Not positive, but I'm like 80% sure that one of these two corollaries shows up on your test. Just so you know.
Awesome.
Because they're good, simple proofs to make sure that you understand this theorem.
Yeah.
So now I'll show you the next one. Or sorry, that was handling the case where A and B are even. So our last case is A and B are odd. If A and B are odd, what do I know?
They're equal to. Did you use m before? You did.
M and N.
Yeah.
So I can say A is equal to what?
2m plus 1 and b.
2n plus 1. And B is equal to 2n plus 1. Okay? Then what?
Their difference
A minus B,
is 2m minus plus 1.
2n plus 1 minus 2n minus 1. Don't forget to distribute your negative to all the B, since we're doing minus B.
So the ones cancel out and you have to add 4.
The ones cancel out, and so we get 2m minus 2n, factor out the 2. That's equal to 2 times m minus n, which gives me that
2
A
divided.
minus B is equal to 2 times an integer, or in other words, 2 divides A minus B, which gives me that A is congruent to B mod 2. And there we go. We did it both ways. There's the proof. There's the end. There's our first section.
That's super easy.
Now, for the love, please go back and make sure you understand this theorem. Very good section for you guys to go back and read. Make sure you understand this. This is setting up the foundations for the rest of the course, the rest of the class. It's not going away. I need you to understand that theorem.
What does the homework look like?
What does the homework look like? I don't know. It's probably mostly easy stuff like this. What we did at the start of the class.
Yes!
Yeah, that will excite you. But I would definitely make sure that you understand how to prove both these corollaries.
Okay.
They're not that bad, you guys. Come on. I'll tell you what, just for you, I'm going to record it, upload it, and then you can watch it, see how it's done, practice it yourself, perfect it. Can't wait to see what you come up with.
Awesome.
Okay, good?
Yep.
All right, so we'll do a quick break and then we'll go over your test.